areas in algebraic geometry. And let me tell you a little more with the new students. So Professor Parameswaran, these are all these MSc PhD students integrated. They are sitting here. And
Okay.
for your information, that Professor Parameswaran was the first director of this institute. He was here for 2 years, and most of the things what you see here, it during his time that has been done. So he's wonderful, and he is of course from the nearby areas. And another thing is that he's the chairperson of our research council. So our council is chaired by Professor Parameswaran, and he's all the help. I myself, Pranab, and Akhilesh, Vijay, always anything we have to take, we talk to Professor Parameswaran. He's a fellow of the Indian National Science Academy, and he's a prolific researcher. I mean, algebraic geometry is not that a thing that one can publish very easily and lots of things. But I was just going through his profile. It's amazing that the kind of work that he has done in that such a difficult area also. Professor Parameswaran.
Yeah. Thank you, Kalyan, for this fantastic introduction. Yeah, with this new initiative and then getting students there, I wish a big success for this whole integrated PhD program. And I'll certainly be behind this too to help whatever the possible thing that you need as well as whatever that I could do. Yeah, with saying these words, let me start straight with the topic. So shall I share? 1 second.
Yeah, it's perfect, Professor Parameswaran.
Yeah, I'll change the view. I'll make it full. Yeah.
Perfect.
Okay. Okay, so today I'm going to talk about some properties of the maps between spaces. And let me emphasize, do not get into very big spaces or other kind of issues, though I will be saying a few words about those. But what I would like generally to say that stick to Riemann surfaces. Many results that I talk about today are also of real interest even for algebraic curves or Riemann or complex numbers, that is Riemann surfaces. So with that short 2 words, let me begin. So I'll begin with what's called projective curve. So do not worry too much about that. So by a curve means something of dimension 1 over an algebraically closed field. And when the corresponding ring becomes regular, it's called a smooth curve. Okay. And when it's also proper, it becomes algebraic. So I will not get into what is a projective space, what's a projective curve. But over the complex numbers, these are nothing but compact Riemann surfaces. So maybe those who know compact Riemann surfaces, keep that in your mind throughout. So for simplicity, you may stick to this whole, most of the cases until the last 2 or 3 slides, you can just stick to thinking of compact Riemann surfaces. Okay. And we wanted to study the property of genuine ramification. So I would talk about what is ramification a little bit, maybe not completely, but étale is more important thing. So which is kind of the complementary. Okay. So let's analyze. So I'll straight away begin with a definition cum theorem. So for instance, just think of 2 Riemann surfaces. Suppose you have got a non-constant map. Okay. Be a separable morphism between 2 irreducible smooth curves defined over K. Then the following conditions are equivalent. The homomorphism of the étale fundamental group. I believe you are familiar with what is fundamental group, comes in topology. And the étale fundamental group is kind of its analog that comes in algebraic geometry. I'll be explaining in the next 2 slides. So this map must be surjective. Second one, F does not factor through an étal cover of D. So what is an étal cover? It's a topological covering. So I suppose you are familiar with what is a covering space. So if I take a Riemann surface, a covering space is the one where at every point the map is a local isomorphism. Okay, and that's precisely the definition of étal. The differential at any point does not vanish. Okay. The third condition is the fiber product being connected. That's another very different area. That's like you take the product, fiber product of C cross C over D. That means you look at the product space C cross C and look at points X comma Y such that X and Y map to the same point in D. That is what is called the fiber product. So the fiber product is connected. And the fourth one, the global sections of the sheaf, F upper star of F lower star OC is 1. So in fact, it's not so difficult to see the conditions 1 and 2 are equivalent, because that's more or less goes in the definition of étal fundamental group. And 3 and 4 will get connected once you know a little bit about this sheaf, F upper star of F lower star OC. So it says something about a space is connected if and only if H naught of the structure sheaf is one-dimensional. We will come to that again. Now, the fifth condition is a non-trivial condition. And in fact, I will be building up along that a few slides soon. It says maximal semi-stable subbundle of the direct image is the structure sheaf. Okay. Now, what is an étal fundamental group? So I'm going to look at each of those terms, many of those terms, and give a quick kind of glance at what are they. Okay. So given an algebraic variety, X, the set of finite étal covers form an inverse system. Now, if those finite étal covers happen to be Galois, then there are some Galois groups associated to that cover. And then you can also see that those groups form an inverse system. The étal fundamental group is defined to be the inverse limit of the above inverse system and denoted by pi1 étal. So now let's just look at the usual topology, what happens. For a complex variety, the group pi1 étal is the profinite completion of topological fundamental group. What does that mean? You take the fundamental group, look at finite quotients of the fundamental group, and that form an inverse system. Take the inverse limit. Because what happens in algebraic geometry is any kind of covering that comes up is automatically finite. If I have an algebraic map, the fibers must be finite. Okay? So you cannot get an infinite cover in algebraic geometry. For instance, even the both varieties could be algebraic. Like you can take a torus and the complex plane and look at the covering map, the universal cover map. But though both are algebraic varieties, the map is not algebraic. It's kind of a double exponential. Okay. So in algebraic geometry, what you can get hold of is only finite covers. That is why one looks at from the usual pi1, you have to keep taking the finite quotients and take the inverse limit. And this is the one that makes sense over any field and vast generalization which comes out of topology, and then purely you can build it with geometric techniques, algebraic geometric techniques. Now, if X is simply connected, then there is no finite quotients. So the pi1 étal also must be trivial. It is still an open question whether for an smooth algebraic variety, pi1 étal is trivial implies whether the actual pi1 is trivial. Whether algebraically simply connected implies simply connected, this is still an open problem. So there are lots of constraints about the usual pi1 even for smooth complex projective manifolds. Now, how do I study these spaces? So now there are other terms which I'm going to bring into like bundles and so on. I'm just giving a two-line motivation for what is really a bundle. How do one do geometry? So the geometry is usually done by looking at functions on a space. But unfortunately, if I take a compact Riemann surface, there are no functions. So what do I replace it by? So I'm going to look at functions in a different way. Functions on a variety are sections of the trivial bundle. That is, you look at x cross k and look at sections means what? It's of the form x comma fx. A section means when I take it into map from x to x cross k and come back must be identity. So the first coordinate is x, second coordinate is fx. So any fx could be thought of as x comma fx. So this is a new way of thinking. Okay. So the functions I can think of local functions in a way. That gives the idea for line bundles. A line bundle is locally linearly trivial fibration. That is, there is an open covering ui of x such that the L restricted to each open set is a product. So the sections are like functions. So they are like local functions patched up together. So the sections of the line bundles, so the concept of line bundle is like studying the functions locally. That's the idea. You may assume that your open sets are, so if you're thinking of analytic, you could also do the Zariski. I'm not getting into that. In fact, let me just tell you one thing. The Zariski open subsets of compact Riemann surface are complements of finitely many points. So the Zariski topology, if you just think it as a point set topology, it's just cofinite topology. But it has much more than that. So I'm not getting into that topology alone. There are much more geometry in it. Okay. A vector bundle is just a generalization. Instead of rank 1, I'll just put k. Instead of k, I will put kn. And then again, on the fiber, I demand linear property. Okay. That's all. So these are the definitions. Now, let me just define the notions of degree of a line bundle. One defines the degree of line bundle as follows. Choose a section L, holomorphic on U. That is like a holomorphic function on U. It's locally trivial, so take any function there but think it inside L and extend it as a meromorphic section. Then count the zeros and poles with multiplicities, sum them up with signs. That's the degree. Example, trivial bundle has degree 0. We all know the meromorphic function on a projective curve has equal number of zeros and poles if counted multiplicity. Other way of saying, sections of trivial bundle are same as morphism from C to P1. So wherever there is a pole, you send it to P1. This is actually a holomorphic map from C to P1. Then every fiber have the same cardinality. So there is nothing very special about 0 and infinity. You could also have a 1, you could also have a 2, you could also have a pi. They all have the inverse images same number. The degree of a vector bundle, if I want, is just the degree of the exterior product. Okay. Now there is a new notion of some new invariant called slope, which is just degree by rank. Okay. So let's go ahead and we'll come back to more simpler cases soon. But let me just take these definitions because unless there are enough definitions, there's nothing that I can do much about it. So a vector bundle is called semi-stable. It's another new notion. If for every torsion-free subsheaf, the slope must be less than or equal to or less than. See, the point is you are on a PID. So every torsion-free sheaf is automatically locally free. So every torsion-free subsheaf F is automatically a vector bundle. So its mu do make sense from the earlier definitions. Line bundles are always stable. Okay. Now, this is the celebrated theorem of Narasimhan and Seshadri. When over complex numbers, a vector bundle on a smooth complex projective curve is stable if and only if it admits irreducible flat projective unitary connections. So this means that the stable bundles that I defined in the previous paragraph page with all those algebraic notions. So there is a line bundle, then there is a vector bundle, then there is a degree. Everything was algebraic. That's directly connected with the topology of the underlying space, the representations. So there is little more. This is only projective unitary connection. If you also assume degree is 0, then it's actually a unitary representation arises from. Another corollary from here is that given a non-constant map of irreducible complex projective curves, the pullback of a stable bundle is stable if the topological fundamental group is surjective. You see, if I have two groups that is surjective, then the corresponding étale fundamental group is also surjective. And if that happens, pullback of stable becomes stable. So stable is one notion from some corner, which is purely algebraic, and this is purely topology, and it gets connected directly. That's the point. Okay. So let me just go back to that equivalent definitions. Yeah, here. See, look at that. The first one was about, the second one is about pi1 étale being surjective, and then something about the pi1 being surjective related to some semi-stability game that's going to come back later. Okay. Yeah, so there is a degree. Now there is something about the home, the sheaf. How does the map of the sheaves look like? If L and M are two line bundles, and the degree is bigger, then the home must be 0. So this comes from the second fact. Let's go by one. Yeah. This is an easy consequence that if M is a rank 1 locally free sheaf contained in another, then the quotient is a torsion sheaf, and the length of a torsion sheaf is always non-negative. And hence you get the degree of M plus degree of the torsion is degree of L. So degree of L is always bigger than or equal to degree of M. As a consequence, if the degree is bigger and the other one is smaller, then the home is not there. That's all. So it's that simple. Every proper subsheaf of a structure sheaf, they are the ideal sheaves, and they have negative degree. Okay? So these are the main points. And as an easy, I will not say why, generalization, we can say that if you have two semi-stable bundles with one bundle have higher mu, then there is no homomorphism. Homes are just 0. What is the use of all this? Using this, I can construct a filtration on every bundle. Given a vector bundle, there is a unique filtration. Okay? So first, there is a unique subbundle. That is maximal subbundle of maximal slope. So it's just set theoretic existence. So there are some subbundles, some numbers are there. I will just take maximal by axiom of choice or something, it actually exists. Then, because the higher mu to lower mu, there is no map. You will prove that you take the beta subbundle, take the quotient, take the beta, take the quotient, take the beta. This is unique and well-defined give rise to a filtration. And this filtration is called Harder-Narasimhan filtration of a vector bundle. we also note the maximal number to be the mu max and the minimal number to be mu min. Okay. Now, direct image. So this is something you do even in anywhere. So what is a direct image? So take a map from C to D, be a non-constant morphism, then a finite. So then the functions locally on C can be thought of as functions on D branched at some point, right? At the image point. So in other words, take a point in D and look at a small neighborhood and look at all points lying in C and look at functions at those points. So the functions in C at those points, it gives like a direct sum at all those points. So this essentially gives the direct image of the structure sheaf F lower star OC as a vector bundle of rank is equal to the degree of the map. So at every point lying above, there is a function. So it will be like a function at one point, other point, it's a direct sums. So it's a power series. So what is happening? Take a point in D, look at a small neighborhood, some small disk. Over that, there are D disks. You look at functions on each of the disks. So you got D disk. So it's a direct sum of D disks, functions on them. So that's the sheaf is the locally free sheaf over the space of functions. Since pullback of function is again function on C, you will see that the OD is a subsheaf of OC. Consequence, and we already know OD has degree 0, trivial bundle has degree 0, and the mu max is at least 0. Now we are going to do the converse. Okay. So for that, I will also assume that there is a direct image for any sheaf, and I'll take that definition, and then you go back the pullback behavior. First thing to note is the F upper star and F lower star are adjoints. So the home F lower star G is home F upper star G. Okay. Since the degree of vector bundle gets multiplied by the degree of the map, and look at from here, what you can really show is that a semi-stable bundle will pull back to semi-stable bundle. It's essentially a consequence of this adjunction formula. One conclude that pullback of semi-stable bundle under finite separable maps remain semi-stable. This is in any characteristic. As a consequence, home of any F to F lower star OD is equal to home of F upper star F OC. Hence, mu of F is less than or equal to 0 for any semi-stable bundle. That shows that F lower star OC mu max is less than or equal to 0. Look at the previous statement. Here we said 1 to 3rd point is said mu max is greater than or equal to 0. And here the 3rd point says mu max is the 4th point. The last point says mu max is less than or equal to 0. So the mu max, the beta subbundle has degree 0. So the maximal subbundle and the étale cover. That's the theorem. Let C to D be a non-constant map of smooth projective curves. If F, the map F is étale, that is its topological covering, if and only if the direct image is semi-stable. It's also equivalent to just checking the degree. It's also if and only if the direct image has degree 0. Degree 0 automatically implies semi-stability. Now, take arbitrary map, look at F lower star O. The beta subbundle can be shown to be, so the first point is that F lower star O is sheaf of algebra because O is an algebra. O is a ring of functions. Functions is as the algebra structure. So the direct image is a sheaf of algebra, and the maximal subsheaf, the beta F lower star O, is a subalgebra. Okay, because the algebra structure comes from the tensor product of the corresponding bundles. And you can prove it is a subalgebra. Now, once you have a subalgebra, I can take its spectrum. So, if we take the spectrum of this subalgebra, d tilde is equal to spec f lower star O degree 0 is an intermediate étale cover. So, I constructed the intermediate étale cover by doing pure bundle theory. Purely from bundles, I identified a subalgebra which represents the étale cover. Comment. Since the algebra makes it harder, as tensor product may not behave well in positive characteristic, still this part of the beta subbundle being algebra provided fairly easily using the fact that we are dealing with structure sheaf. So to analyze further the behavior of the pullback of stable bundles, we need to understand the structure of F lower star O mod the maximal, the beta subbundle, also F lower star O mod the O itself. Okay. Now I'm going to relate it with the topology of the fiber product. So look at the fiber product. What is fiber product? It's set of all x comma y such that fx equal to fy. And the tilde denotes the normalization. You just separate out the branches. And if any branch is singular, you also normalize. But here you can prove that every branch is actually smooth. Only thing is they may be intersecting. Okay, so it's just separating the branches. Is the normalization of the fiber product. We have this commutative diagram. So what happens? So you take C to C and F, again C to C and F, and look at the C cross C over D and take the fiber product. So this diagram is commutative. Not only that, this pi 1, pi 2, this is actually flat morphisms and this is a fiber product. So you have got what is called the flat base change. By flat base change theorem, F upper star of F lower star OC is nothing but pi 1 lower star of pi 2 upper star O. But the structure sheaf always pull back to structure sheaf. So pi 2 upper star O is the structure sheaf of, in other words, it's a trivial bundle of O C direction C over D and take its fiber, its direct image. So the push down pull back is same thing as the direct image of the fiber product to C. And this is a finite map and the cohomologies are the same. So where I do here or there, and this connects. H naught of F upper star F lower star O is H naught of the pi 1 lower star of this, which is same as H naught on the fiber product, the structure sheaf. See, now you see this last object, it just counts the number of components. Just counts the number of connected components. If I have a connected projective variety or connected compact space, let's say connected compact Riemann surface, not Riemann surface, it's a union, could be singular, but because of the compactness, there are no global functions. So the global functions on such an object is equal to the constants which come from each connected component. So this counts, this H naught counts the number of connected components. So now the Galois property. So now I'm going to look at morphism. This is something interesting, even for those people who do Riemann surface. I'm telling you that C cross C over tilde is smooth irreducible projective curves. The number of components of this is equal to the degree if and only if the map is Galois. There is another algebraic way of saying, let's Kc and Kd denote the function fields of C and D respectively. Then the extension is Galois if and only if the total quotient Kc tensor Kc over Kd is isomorphic to direct sum Kc. So there is no extension of Kc is shown up there in the tensor product. So this is something very interesting. And there is another criteria for checking Galois. Proposition. C to D is a non-constant separable Galois morphism of degree D between irreducible smooth projective curves. Then F upper star, F lower star OD mod OD is a coherent subsheaf of the trivial bundle OC direct sum D minus 1. So this is one of the important starting point of analyzing this subsheaf, the F upper star, F lower star mod OD. So the point is this OC is sitting inside here, it's also sitting inside the trivial. The point is, how do we get this putting in that trivial bundle is by putting pi 1 tilde lower star of OC tilde. Let's look at the map. See this C tilde was union of, so in the Galois case, union of disjoint union of the curve C itself, so many copies. And in fact, those copies are identified as tensor with the Galois group gamma. Okay, so this is nothing but C cross gamma in some sense. Okay, in a very canonical sense. And using that, you get how to put this, and then you see this OC, which is sitting here, will go to the canonical OC, which is given by OC tensor 1 in K gamma, where K gamma is the functions on gamma. Now, this implies the direct image, okay, is isomorphic to this F lower star F OD is inside the trivial bundle of rank 1 less, because this OC actually splits go into that one factor. The structure when it's genuinely ramified. This is the most crucial observations that we did recently. Okay, so let's say F from C to D a genuinely ramified Galois morphism of degree D between irreducible smooth curves. Then this pullback is contained in the direct sum of line bundles, and each line bundle have degree negative. We do not know whether this itself is a direct sum of negative degree line bundles, but they go inside. What is the consequence of this? For any semi-stable bundle W, the mu max of the tensor product with that quotient is always strictly less than the mu max of this. And that implies the homes are 0. And what is the consequence? Consequence says the home of two bundles on D, okay, is the same thing as the home when I pull back. Okay? And the proof is just the adjunction that we said earlier. F upper star W home is same thing as home of V with F lower star F upper star W. But the second one by projection formula is W tensor F lower star O, and this is home BW. And to say this last sequence is where I have done all this work. So all these works were needed to say the homes are same for semi-stable bundles of same slope. Okay. Now, how do we get this? So now I wanted to come to this. So this was one of the major crux of the matter for analyzing the morphism and the behavior of stable bundles. So the question that we were looking at in one sense is, when does all stable bundle pull back to stable bundles somewhere? So as we already saw, it's very closely related with topological fundamental group over complex numbers. If you use that, what do I say, the Narasimhan-Seshadri theorem, then it's nothing but the profinite completions, the behavior of that under the map. Okay. Now, to obtain this, so actually Narasimhan-Seshadri theorem is a deep theorem connecting the topology of the curve with stability of the bundle. And we are even working in higher characteristic, arbitrary characteristic over algebraically closed fields, and we don't really have the topological fundamental group. So I can't use any characterization using topological fundamental group. At the most, what we have is étale fundamental group. But that wasn't sufficient to get a statement of this kind in the beginning. So how do I get this proposition? This is another very interesting geometric construction. Now, you can think you are on a compact Riemann surface. This is already very interesting even for compact Riemann surface. Take a map from C to D, which is genuinely ramified between the complex projective curves with the Galois group gamma. Now, we will give an ordering of the Galois group. Okay? So, we will give an ordering. So, we will order the gamma in such a way that the elements are gamma 1 to gamma d, and there is a map from 1 to d to 1 to d such that. So, now the gamma 1, I take it to be the identity. Okay. So let's look back. So what is the idea? So okay, let me give the statement first. So gamma 1 equal to E, and eta 1 is equal to, the eta map is like eta 1 equal to 1. And then you put all the first few numbers, they intersect the identity. So what is gamma 1? So let's look at the C gammas. Okay, so what is a C gamma? Let us look at the fiber product. Fiber products are indexed by the Galois group. How do they get indexed? So a curve C gamma is a component of C cross C over D by the points x comma sigma x. So call this C sigma. Okay, so this is a component. I have a map from C to C cross C over D and look at its image, and that's a component, and I call that C sigma. So all the components of C cross C over D are of the form C sigma for some sigma. So what is C identity or C1? C1 is nothing but x comma x. That is the diagonal. So now look at the first condition. So the gamma 1 is 1. Okay. So now you look at all the gammas. So look at the, so now, so I look at the next set of all gammas which intersects the diagonal. Okay. Take all of them and then send all of them to 1. Now, if this already exhausted all your gamma, your process is done. Now, we use the fact that C cross C over D is connected. Once C cross C, the fiber product is connected, now you look at all the components that intersects diagonal. If it doesn't exhaust all, what it means is there is another component which is not diagonal, and there is a third component which intersects that but not the diagonal. So now you start filtering in this fashion. Now you start naming that second component that I pick up. Let's call it 2. And then you look at all components that was not intersecting the diagonal but intersecting the gamma 2. Now, if all this collection became the whole gamma, then again you are done. If not, what will happen? There is a third component which doesn't intersect either diagonal nor the gamma 2, but it intersects another component that intersects C gamma 2. You do this process, and that gives you the map eta and satisfying these condition 1, 2, 3, 4. And this process will end because your fiber product is connected. So this is another beautiful way of giving a filtration, giving an enumeration on your Galois group to understand the topology of the curve and the map C to D. Okay. If now, so in the non-Galois case, so okay, so with this, so and then I have not really worked out the details of the rest of the part. From here, you have to again do a non-trivial work. So what you need to do is you go back here. So you already put this quotient inside the trivial bundle. Now, using these intersections and changing the way the trivialization of OC to the D-1 factors, I make sure that the images of these are go purely into strictly negative ideal sheaves. They are non-surjectives. Once you do that, so suppose I make sure that this sub-sheaf projects to ideal sheaves of this, then you can easily prove that this sheaf itself is sitting inside the direct sum of those ideal sheaves. And to obtain those ideal sheaves, that's where I wanted this enumeration. So to make sure that I will make sure every curve, there is a point where the difference actually vanish. So the projections are essentially given by, let's look back. So the projections are essentially given by those C sigmas itself. So on every C sigma, you will see that this object, pi over star OC mod this, its image will vanish at some point. So it is this vanishing that is obtained by this enumeration process. And if it is not connected, this enumeration process cannot be done. And H0 do shoot. Okay. So this is for not the Galois case. This already takes quite a bit of work to prove this statement. And for the non-Galois, it's actually much worse. You have to go to the Galois closure and analyze it there and get these pulled back there and analyze how it sits there. And then there is a little bit of non-trivial works out there. Okay. We conclude. Okay. So once we have this theorem, then we can conclude. So what is the theorem? So essentially the theorem is about this home, that mu max of W tensor F over star OC mod OD is strictly less than mu W. This is what finally one proves for any genuinely ramified maps on for any semi-stable bundle. Okay. And from there we conclude that the homes are same, and then stable pull back to stable, but it will need much more harder work. Okay. So this was our aim. Actually, there is more. In fact, we even proved that if you get an étal cover, then there is a line bundle whose push down is stable, but its pullback is not stable. So in fact, so this genuine ramification property is actually characterizing the morphisms which satisfies that every pullback is stable. Now let me say a little bit about higher dimensions. So this genuine ramification, as it is the definition, had worked it out long back with Subramaniam, and then we had some work, and then there were some steps, some lemmas which we stated there, which we just had some proof and later realized that there is a gap. We have not given the complete proof, and that's what really we worked it out and completed now. It was much harder. And in higher dimensions, again, that part of the gap is still there, but there were many other things were worked out with this. So in higher dimension, what happens? So what was the main point here? The point is when I take f to x a finite separable morphism of smooth projective varieties, the analog of 5 conditions about the ramification that I wrote down. Okay? The slightly hard one is the definition of the maximal semi-stable subsheaf of the direct image. And in fact, you have to prove. So first of all, I have to define semi-stability. I have to define what is the, so in higher dimensions, I haven't done anything, the degree, slope. So all these have to be defined appropriately. We can define all those and take for any polarizations, doesn't matter. And then you can take a flower star, and then one can prove that the degree 0 part actually form a sheaf of subalgebras. This was a joint work with Balaji long back. And here, the main ingredient was to observe that whenever you take a finite map of smooth varieties, the branch locus is a divisor. So the degrees, when I go modulo the degree 0 part, the rest of them have really negative degree. Yeah. So now the work that is in progress. Now I am trying to show you some difficulties that one come across when you go for normal projective case. So when I take a map between finite separable maps of normal projective varieties, the analog of 5 conditions of genuine ramification holds, but for the last condition. The last condition of that maximal degree 0 being O is not quite correct. And that's not sufficient. So we'll just show you an example. The reason is, since étal covers give rise to locally free direct images, and maximal subsheaves of étal coverings are not the same. Maximal subsheaves usually are not locally free. So let us look at this example. Consider a finite group acting on P2 freely outside a set of finitely many points. Then the quotient is a semi-stable sheaf of degree 0. That's because on outside finitely many set of points, this is an étal cover. This is a proper covering, even over complex numbers. Okay. So once I have a proper covering outside some finite set of points, this is actually on a big open set, this defines a covering. And the covering, so with the degree, with that, so essentially it goes back to this statement here, and that holds true. So which one is it? Yeah, not this. Not this. Yeah. This statement on a big open set start working, that some map is non-constant of smooth. In fact, now projective varieties, I can remove the curves to varieties and say étal if and only if this has degree 0, and this works on so-called big open sets. That means outside codimension 2 of a variety, and that is what is happening when I take P2. Yeah. See, when I take P2, it acts freely outside finitely many points. So the points of codimension 2. So on the big open sets, it's actually a free action. So the quotient is well defined. Okay. Hence the semi-stable, the direct image will be semi-stable of degree 0. So the issue here is, if I look at the direct image as the O from P2, this is not a locally free sheaf. It picks up a purely reflexive sheaf which is not locally free. So we needed to identify what causes the étalness inside the direct image. So this is a work with Indranil Vishwas, that FBA, in fact, even the first part that I said about curves is also work with Indranil Vishwas. Okay. So let F be a reflexive semi-stable sheaf on X. There is a unique subsheaf satisfying the following conditions. V is polystable, that means a direct sum of stable and sheaves. And this is the quotient is torsion free, and V is maximal among all such sheaves, subsheaves. This is called the socle. Okay, and it's called reflexive socle for the time being. Warning. For torsion sheaves, torsion free sheaves, socle F does not exist. So if I take a torsion free sheaf, it does not exist. But what we have here is for a reflexive sheaf, it exists. So the point is F lower star O is a reflexive sheaf. Again, that's not enough. To identify the topological coverings, we need the locally free sub there, and that is our research. If F is a reflexive semi-stable sheaf on X, then there is a unique coherent subsheaf satisfying V is locally free, polystable, that's direct sum of stable, and the quotient is reflexive. And V is maximum among all locally free sheaves satisfying the above two conditions. This is called locally free socle. And the point is there is a locally free socle exists in the normal projective varieties and for every reflexive sheaf. So this is apart from the harder Narasimhan filtration, which again exists, but that's not sufficient. We need much finer invariance, and that is what doing the jump. Theorem that f from x to y be a finite separable morphism of normal projective varieties, then f lower star ox 0 LF, that's defined here. This is what I call FLF. FLF is if I take a semi-stable sheaf and look at the maximal locally free socle and then keep extending. Look at this, including taking extensions, inductively taking extensions of locally free sockles of successive quotients. We obtain a unique locally free subsheaf FLF. So I proved that locally free socle exists. Now you take the quotient, there again a locally free socle will exist. Then I have to take the pullback of that locally free subsheaf. So it will be an extension of locally free by locally free. That will be another locally free on the total space. So you have to do this inductively to produce a maximal locally free subsheaf of F of the same slope, and it's called FLF. Take that object for F lower star OX degree 0. And it's contained in the beta subsheaf, the harder Narasimhan subsheaf of F lower star OX. And then you take, so this is the last one, the F lower star OX 0 LF is a subsheaf of subalgebras whose spectrum provides a maximal étale subcover of F. So this gives the relation between, given a normal variety of the finite separable morphism of normal varieties, how do one extract maximal étale covers of this map? Okay. Now from here, again we need to do what we did even for curves and the smooth cases. Now one can repeat many of the steps. We are still not completed about one step, about getting that the relation with H0, the connectivity of the fiber product, and the genuine ramification. And the place we are not really stuck, we already have all the ideas. And so the point is that here what we will get is not that F lower star O, F upper star O, F lower star O mod this FO is not just contained in direct sum of negative line bundles, but contained in ideal sheaves. And the point is, a vector bundle can never map to an ideal sheaf. So again, the idea is the home is 0, and then you get the proof that, and then of course you have to do all the other works also, standard works, but these are the most technical work involved. And then you can prove every stable bundle will pull back to stable bundle. So that's why I said it's work in progress, and hopefully it will come up soon. And with that, I end my talk. Thank you.
Yes, thank you so much, Professor Parameswaran. And now it's time for the audience here in the seminar room first, if they have any question. We will move into the other part. Is there any questions? Okay, so is there any question from the Zoom attendee?
No, no question from YouTube channel.
From YouTube channel too?
No
Yeah.
questions.
Thank you so much, Professor Parameswaran. It was really a pleasure to have you with us. And of course, we wanted you to be here during these things, but I know it's not that congenial right now. But hopefully you will be with us very soon. And
I too hope so.
so hopefully things will improve, and we all will be here at KSOM and fix up the future strategy, and the students also will be eager to meet you. Thank you so much, sir.
Sure. Yeah. Thanks.
Bye-bye.